So one of the things you'll have to understand how to read are these standard reduction potential tables. And notice on these reactions are all written as a reduction half reaction. There are no oxidation half reactions written on these tables. And that just keeps it easy to understand, and then you don't have to worry about which ones you're reading, whether it's oxidation or reduction. But you should be able to understand that by looking at the reaction. But let's just look at these real quick and show you what I mean by that. So all of these here, these reactions, are reduction reactions. Notice that they're all adding electrons. So we're going from a higher oxidation state to a lower oxidation state. And if you look at this column here, the oxidation state of the, let's say, lithium metal here, is lower than the lithium ion. So therefore, we're going from a more positive oxidation state to a lower oxidation state, which means that we are doing a reducing. And then this is the energy associated with doing that reaction. So in some of these reactions, you can see when we talked about positive energy, the positive energy means it's spontaneous, and then if it's a negative energy, it means we'll have to add energy to it to make it work, right? And that makes sense because it says here that it's more, let's say the lithium ion here, it's more energetic to be in the lithium ion state than it is in the lithium solid state. We already know that lithium solid is very difficult to exist in nature because it wants to give away that electron, and therefore the negative energy says that if we want to have the lithium solid, we're going to have to put some energy into it to make it work that way, right? So another way to read this thing also is these are going to be their strong oxidation agents here are the ones that are going to be most easily reduced. These are our weaker oxidation agents, which are the ones that are going to be most easily oxidized. And then, on the flip side here, you have a strong reducing agent, which means these are the ones that are going to be more oxidized quicker. And then the weaker ones are going to be up here. So these are the ones that are going to be very poor reducing agents. These are strong reducing agents. So these ones here are going to be the ones that are least likely to be oxidized. Okay, so now you have an understanding of the table, and we can use the table to make predictions of what the E0 of a cell was based on the oxidation reduction reactions of the two components that go into the cell. So let's see how we do that real quick. And I'm going to do an example with you right now, and then we'll explain how we're going to use the rest of this to do it on your own, and then I'll come back with the answer. So let's just do the first one real quick here. So we have to figure out which one of these is being oxidized first. So remember, any lone metal and lone compound are going to be oxidized. So both on these, the oxidation states are going to be 0 to start out with, right? And then we go over to the other side of the equation, which is our products, and now we have to apply our rules. Now our rules say that any alkali earth metal is always going to be +2. So we're going to put that +2 there for the magnesium, and then therefore the chlorine has to be -1. And since there's two of them, we're going to get our total of -2. Right? So remember that there are two chlorines. See the two there, but each chlorine is only -1. It's not -2 chlorine. All right. So now let's write the both half reactions. So let's do the first one. We'll do the oxidation reaction. So we're going to write magnesium. That's 0 goes to magnesium 2 plus, +2 electrons. And then now let's write the reduction reaction. Remember, the reduction reaction goes from a higher oxidation state to a lower oxidation state. So we have Cl2 plus, and now we're going to put our 2 electrons because there's 2 of them, and it goes to 2Cl minus. All right. And now you can see that the 2 electrons are going to cancel each other, and then our net equation is the one we have on the top there. Okay. Now we have to look up the EMF of all these. So let's look at that real quick. Okay, so back on those tables that you can look at, we know that for the reduction reaction, magnesium 2 plus 2 electrons giving you magnesium 0, that was minus 237 volts, 2.37 volts. So let's just write that here now. But since we're going to have to do it again, it's going to be flipped. We're going to have a minus 2.37 volts. You can look on that table that we just did on the previous one. And then the chlorine one was 1.36 volts, and that was positive, and that was the general reaction, because don't forget we're reducing. This is our reduction reaction, right? Let's just write that down here. So this is ox and this is reduce. And so the way it's written in the table is correct as far as the voltage, and that's 1.36 volts, right? And now we just got to multiply and add them together. So we multiply negative times a negative, so we get a plus 2.37, and then we're going to add that to the 1.36, and our total number is going to be 3.73 volts. So we would put 3.73 volts here. So what you should try to do now is copy these down, these three equations, and then stop the video and then scroll back until you can see that table, or use the table that I gave you in class, and then work through which one of these is the oxidation reaction, which one is the reduction reaction, calculate the voltages for each half reaction, add them up, and you get your E0 for your total reaction. And don't forget to write the final reaction on the bottom, balance it for both charge and a number of atoms, right? And I'll return with the answers in the next slide. Okay, here are all the answers to the questions that I just gave you on the other one. So we already did the first one real quick first, but remember that when you write your final equation, it has to be properly balanced and has the correct number of species. So here, magnesium metal chlorine gas, and then are going to get magnesium chloride solid. So it's not existing in ion form anymore. The second equation is kind of a little bit of a trick, and let's see if you understand what's going on. So here's my basic ionic equation, right? I got copper metal going to copper 2 plus. I've got silver ions going to silver metal, and these are probably done in some type of solution. And so I'm going to write my two half reactions here. Here's my oxidation reaction, and then here's my my reduction reaction. To balance them, I need to multiply the reduction reaction by 2, because my reduction reaction from Ag plus to Ag0 only requires 1 electron, but I need 2 electrons up here, so the electrons must balance. So I'm going to multiply everything by 2, and then so my overall net equation for the reduction equation is going to look like that. And now I put that on this side here, and now I can cancel the 2 electrons here and 2 electrons here to get my overall reaction. Now notice what happened though. When I looked up my table for this one, I got 0.34 volts, but since this is a oxidation reaction, I have to flip its sign, so I added a negative. On this equation here, Ag plus to plus 1 electron gives me Ag0. Now that is a reduction equation, so the number I'm going to use is right off the table. But notice I did not multiply it by 2, even though I multiplied this by 2. The voltage associated with a reduction or an oxidation reaction is an intensive property. It does not matter how much material is being used or or the coefficients or anything like that. It's an intensive property, just like density is an intensive property, melting point. It's irrespective of how much material you'll have there, right? The melting point of 100 grams of ice is going to be the same as a melting point of 1,000 grams of ice under the same conditions. So therefore, we do not multiply the voltages in any case, right? So the voltage is going to be 0.8 0.80 volts. If I have to multiply this side of the equation by 40 or 2 or 1 or whatever, it's just going to be 0.8 volts, right? So when I've looked up all those voltages, I have the voltage for the oxidation reaction of copper to copper 2 plus as being 0.34 volts. That's for the reduction reaction, but I had to flip the sign since it's now an oxidation reaction, and it's -0.34 volts. The reaction of silver ion to +1 electron to give me silver metal is 0.8 volts, and that's directly off the table. So my net overall is 0.466 volts. I had a negative in there, my mistake, so I corrected that. So overall, the total EMF of that cell, or the voltage for that cell, is going to be 0.46 volts. And again, on number 3, the same basic principles apply of number 2 and number 1. We have to figure out which reaction is being, which materials are being oxidized, which ones are being reduced. So we know we're going from here, which is lead, that's going to be lead 0. And up here, lead's going to be lead +2, so that's going to go from 2 to 0, so we need 2 electrons to do that. Aluminum starts out at 0, goes to +3, so there's my oxidation reaction, right? I need to balance both the charge and the atoms, so I have to multiply one side by 2, one side by 3. My overall net reaction is this when I'm done canceling the electrons. And again, I don't multiply the voltages, and I add the voltages up, and I've got 1.53 volts for that. All right, and you can do the same on the last one. So that's pretty much it, how you have to set these up using your table, making sure you flip the voltage sign if it's going to be an oxidation reaction, because all those reactions are written as reduction reactions. Then add up the 2 voltages for both the oxidation and the reduction reaction to get your E0 for your cell. So here's your Voltaic cell. It basically consists of a container of this material here, which is going to be where our cathode is. This is our container where our anode is. And then in each container we have the actual metal strips. Here's my copper and here's my zinc. And then a solution of an electrolyte. In this case, it's zinc sulfate, and then copper sulfate on this side. And then we have this thing called the salt bridge. And in this case, the salt bridge contains a ionic species that has both the cation and the anion. And the species are chosen so that the cation and the anion don't interfere with the redox equations, right? And then the last thing we do is we connect it through a wire, and the wire allows the electrons to flow, whereas the salt bridge will allow the ions to flow. So the electrons flow through the wire, the ions flow through the salt bridge, right? And let's see how this works. So now my 2 reactions that are going on here, my copper is being reduced to copper solid, so therefore the copper ions are coming out of the solution and going into the copper metal, and that's where my cathode is, right? My cathode is going to be positive, and then my zinc is my anode, and that's going to be dissolving, so my zinc metal is going into solution. So my zinc metal is going into solution, losing 2 electrons, traveling over to the copper side to make available the 2 electrons so that I can react with the copper ions and then for copper metal. So over time, the copper is going to get bigger. The cathode is going to get bigger. Remember, the red cat gets fat. Reduction is going to happen here. And then the anode is going to get skinnier. It's going to get dissolved, get smaller over time. And then I just write my 2 half reactions. I calculate my voltages from my table. I write my general overall reaction here, and then I calculate my voltage, right? So this is how you would see it set up as a one particular way to represent it onto a literature or something like that. And the key components again are the side for the cathode. You have your strip, you have your salt bridge, you have your side for your anode, here's your strip for that, and then your electron would be carried through a wire, right? So all these components would be needed to graphically represent a Voltaic cell. Now another way that you will see this written for a Voltaic cell is the following. Typically you're not going to see that big image that you saw before. You're going to see something written just like this, and I'm highlighting that with my pen here. You're just going to see these types of things. You're going to see copper, some type of metal, solid, going into a metal aqueous solution with a bar in between. Then there's a double bar, and then there's a aqueous metal ion, or aqueous ion, sorry, and then a solid part of that. So that's a solid species. And the way to read these is basically the following. The anode is always going to be listed first because that's where your oxidation reaction is going to happen. So you're going from a solid to a liquid version of the ion, and then from the liquid version of the ion back to the solid for the cathode. So it's anode, cathode are written that way. So this is our anode, here's our cathode, and the double line in between represents the salt bridge. So our half cell is this side for the oxidation reaction, our half cell for the side is for the reduction reaction. So you would just basically see it written just like this, without the red, with all of this stuff on here. And you should be able to understand that this is my anode because it's going from solid into solution, and my solution one is coming out and making the solid on this side. So we have talked about two different types of electrochemical cells. In the first cell, which we've spent most of the time with, we're calling that the galvanic or the voltaic cell. And that's where we take stored chemical energy and we convert it into electrical energy, which we then can use to do work, run a motor, run a vacuum, things like that, light a light bulb. And we do that via redox reactions. So a half reaction for the reduction, half reaction for the oxidation. That overall net is a redox equation. And remember that at the anode, what we're doing is we're taking electrons from this side of the anode, and we're doing the reoxidation, and the electrons flow up here, flow across here, and flow here. And then now they're available to take material out of this part of the solution and go back onto the cathode. So the red cat will get fat, remember that? So the cathode is going to get bigger over time. The anode is going to shrink over time because as this material releases electrons, it goes into solution. As this material gains electrons, it comes out of solution. Here's my salt bridge, and so our net flow is this way. Don't forget that the cathode in this case is going to be labeled positive and the anode is going to be negative. On the electrolytical cell, or the electrolytic cell, we're going to have to input electrical energy, and then we'll take that and convert it back into stored chemical energy via another set of redox reactions. And let's see how that works. So now we add energy to the cell. And notice that there's no salt bridge here anymore. It's just a liquid of, let's say here, magnesium chloride, right? Or magnesium dissolved and chlorine dissolved in a solution. And now when we add the electrons, the flow of electrons is going to go to the cathode. Because what we want to do is we want to do the reduction reaction at the cathode and pull material out back onto the cathode. And in order to do that, if we want to get the material that's normally wants to be oxidized back on the cathode, we have to do the reduction reaction, and that means we have to add energy to get that to work. On the other side, on the anode, we're going to actually be doing oxidation, right? Because we're going from a minus to 0, so that is oxidation, even though it's minus, right? We're going to more positive. and therefore we're going to do that reaction at this electrode. And again, there's no salt bridge here, right? So the cations will move towards the cathode, the anions will move towards the anode, the reduction or the oxidation reaction will occur, and then we need to do that, we need to supply power. So this is how we will do electroplating of like spoons and things, metals. It gets electroplated this way. Rechargeable batteries would be used this way. We have to put energy into it to drive the reaction to the reverse. Okay, here's another representation of both a galvanic cell and electrolytic cell. And notice the changes that occur, right? This side, we're getting energy out, so that's why it's positive, it's spontaneous. And then when it's spontaneous, we get that energy right away, and we can use that voltage to do work. Drive a motor, light a light bulb, something like that. So basically, this is your setup of your battery. Now, if you had a rechargeable battery and you needed to recharge it to get the reaction goes to completion on this cell, and you've dissolved most of your copper, and you've actually got most of your copper out of solution and most of your metal, iron metal in solution, and now you want to recharge your battery. You would have to flip. You have to add voltage now, or excuse me, add a voltage and flip the electron flow. So now the electrons are they're still flowing from the anode to the cathode, but you want them now to flow from the copper side over to the iron side, and therefore the iron would come out of solution and the copper will go into solution. So in that case, the copper is coming from here into here, right? Because that's what this reaction says. My copper is going from here to here, and my iron is coming out. Whereas remember, in this case, the copper is coming out and the iron is going in. So we have reverse. So that's going out, this is coming in. In this case, this is going in, that's going out. All right. So, and when we do that, we need to add energy to make that those reactions go in the opposite direction, and therefore that's why we have a negative 0.7 volts. It's not spontaneous. We need to add that voltage in the reverse direction, so we need to add 0.78 volts, and the negative just tells me that I need to add it as opposed to getting it. So those are quickly the differences between the two, right? In one process, you're getting energy out. If the reaction is spontaneous, we'll get positive voltage out. And the other one is to drive the reaction the other way, we're going to have to add voltage, and that's why it's negative.